Hello. For my course project, uh, I will walk you through the approach on how I have analyzed the problem, how the various models could be used to address this problem, the analysis part, and the metrics that I've used to evaluate the performance and also the nature of this problem will be considered to determine which model would be the superior one to predict the output based on the actual real-time data that we currently have. So to just cover the overview of this problem statement, we have four factors, four features, or I would say possible final feature set, which may or may not determine the final output, which in this case is the net hourly electrical energy output. So let me start with our first model that we have considered to evaluate whether it could be used to address our problem or not. In this case, since it's a forecasting problem, we thought a linear regression model could be the best approach because this one is very much useful in forecasting problems as there are multiple variables involved. And since this is not a simple two variable or one variable problem, we have multiple variables. We are planning to use a multiple linear regression model. And another good thing about this one is it's a simple and interpretable model. If we want to explain this to someone, we can easily do so. And also it's computationally efficient. But there are some risks associated with this model. One is if there is any uh, dependency between any of those variables, or that it could result in multicollinearity as well. Uh, some of the variables could be easily explained by one or more other variables. We need to check that. And if, if it is purely linear or close to linear, then this would be the best approach. But before that, let's do the nonlinearity test and then design. So uh, the output performance metric associated to this model is square, and also we have a mean square error and a root mean square error. So the analysis of linear regression model is shown here in the slide. So we are first determining the correlation between these factors with respect to the output. Uh, the ambient temperature in exhaust vacuum, though those are negatively correlated to the output, but they are strongly correlated here. And if you consider the pressure and humidity, they are moderately or weakly correlated. And the last two factors could be worrisome because it shows some degree of uh, weakness here, and the AP and RH weakness might suggest some nonlinearity. We have also plotted the residual versus predicted values for this model just to check if all the uh, residual values across the predicted values are converging around the zero line. That's a central line. But as you can see here in this image, let me show the Excel data as well. Yeah, here we have this Excel of all the data points, and we did the multilinear regression analysis. Quickly jumping to the scatter plot here. The x-axis denotes the predicted values and y-axis the error. We can see the residual values are swaying between the plus 10 and minus 10 line, which is not a good sign. So this could be another symptom of the nonlinearity. So let's consider the next model, which could be a better fit for our problem. Uh, that is the polynomial regression, which I will cover in the next slide. Before that, I will close by saying that the R square value is 0.928, uh, which is close to 93%, and MSE is 20.778 in this case. Moving on to the polynomial regression model, we try to determine whether the nonlinearity of this in this problem could be effectively solved by this polynomial regression of various degrees, say degree 2, 3, and 4. Uh, and we found the R square and MSE for all those various variations. We can see that all the R square for degree 2, 3, and 4 coming around 0.9394 and yeah, 943. So there is no much R square variation or improvement if the degree is increased. But we also know that as we increase the degree, the complexity of the model increases. So it's not worth the effort to increase the degree to get a more metric performance in this case. But it's obviously it is more uh, suitable than the multilinear regression, as you can see from slight improvement in R square. We are also going to see whether any other algorithm could be a best fit, whether uh, any algorithm that could effectively increase the R square and reduce the error. If you analyze in those lines, we find that one of the algorithm that can be used suitably for both the linear and nonlinear problems would be the random forest regression model. And the forecasting problems with many variables can be effectively solved by this algorithm, or I would say predicted using this algorithm. So we are trying to determine what are the hyperparameters for the random forest regression analysis. We have taken the number of trees as default 100, max depth as 10, and minimal sample per leaf as 1. It's an ensemble based model, and we are using strategy of k-fold validation set based uh, training, and then we are using around approximately 20% of our data for the actual testing. So the k-fold validation will translate to approximately 1531 records in each fold, and there are 5 iterations. In each iteration, one fold will act as the validation set, and the remaining 4 folds will be the training set, and we are going to repeat this process 5 times by just shifting each fold and considering that as validation set and remaining as the training set. If you see the R square and MSE value, the R square has considerably improved. It's 96%. MSE is around 11. If you remember, we started with an MSE of 20 for multilinear regression, and it considerably improved so far. And one more observation here we could see is if you see the R square and MSE for the uh, cross validation set and the test set, they are more or less same, which indicates a good fit, not an overfit here in this case. So that is a very good sign to avoid overfitting scenarios. So we are going to the final section of our analysis where we are summarizing all the models that we considered, the various model performance metric that we have evaluated, and what are the key considerations uh, we recorded in each of those model analysis. So multilinear regression is a good regression model, but it has it has high interpretability, but it doesn't handle the multicollinearity or linear non-linearity problems that well. And going to the polynomial regression, there is also a regression model. It is good to apply for the non-linearity problems. It has slightly increased our R-square and MSE metrics. And I also mentioned the logistic regression. Why it's not used because it's a quick misfit because it's applied only for classification problems, and our case is a regression problem. The final thing, which is the most suitable models and which can be used to predict our future uh, output would be the random forest regression, and this can be applied both for linear and nonlinear problems. It handles multicollinearity really well, and based on our results, the overfitting risk is far low, and the R square is 96%, which is good. And we have a test MSE of close to 12. So random forest regression is the best model for our problem. Yeah, that's all from me. I hope uh, the key aspects of our problem analysis, model selection, and execution are covered. Thanks, everyone.